Hello, everybody. Welcome on our Idea StatiCa webinar on topic how to design the pre-stressed beam with openings easily. Today's presenters are Lukáš Juříček. Hello, Luky. How are you?
Hello, Petya. Hello, everyone. I feel fine. Looking forward to show you what we have. Let's say some updates in concrete, pre-stressing. So looking forward.
That's great. And myself, Petra Komárková. Both of us are product engineers, so you can know us from these webinars, our events, and, for example, help desk. Before we get to the actual content, first organization stuff. We are using GoToWebinar application for this. You are muted for the whole session. If you have any question, please type in the question pane or in the control panel, and we will answer you right now during the webinar or at the end, or if we miss it, we can answer you via email. Let's go back to our topic. So today's topic is about pre-stressed beams with several openings. Lukáš will guide you through the whole process of modeling, designing, and code checking of pre-stressed beams. We will talk about the codes. The main focus will be on pre-stressing in Idea StatiCa detail. So we will demonstrate you how to model pre-stressing tendons, especially the pre-tension ones. And also we will talk about pre-stressing losses and all the things which are related to pre-stressing. So Luky, the floor is yours and you can continue with the presentation.
Thank you, Petty, forward. I will take presenter. Hope you will see my screen in the full screen. And we can start. So today's topic is, I was mentioning, pre-stressed beam, pre-tensioned beam. This is a saddle beam with many openings. I will try to describe the geometry at first. The cross section is standard T section with the height at the beginning 900 millimeters and some linear haunch to the middle, where the height is 1,800 millimeters, and the beam is has a symmetry plane in the middle, so it's symmetrical beam. The total length is 24 meters, so it's a long span beam, simply supported. The maximal diameter of the hole or of the opening is 1 meter in the middle, and the other openings are having 800 millimeters, and the distance is 4.5 meters from the left and from the right part of the beam, and also 6 meters. How I mentioned before, it's symmetrical beam, so everything should be in the axis of the symmetry. Yeah, let's go into application. I will launch Idea StatiCa detail version 21.1. I will start a new project, and I will create a new project. The small window pop up with the selection of the templates. The code check will be according to Eurocode. I will select concrete grade. It's high concrete grade because we are using a pre-stressing, so we have to use it. C50/60 standard reinforcement B500B, and you can see here is a tendon. If I click on these three dots, we have a really big library of the tendons where are material properties and also the diameters of the tendons. So what we use the tendon. It's a standard or typical tendon, Y1860 S7, diameter of the strand 15.7 millimeters. The global cover is 25 millimeters, and what I will do, I can create beam from the templates, or I can use some general input if let's say I have some more enhanced shape or more enhanced geometry, so I can use the import from the DXF, also for geometry and also for tendons. But we have a really simple geometry, so I will create or use a template and use the end support. Right now the processing of the templates. We will get some detail with the trimmed end. What is really important to mention is that tendons cannot be used for the structures or details which has this trimmed end. It means you have to get the complete geometry without the trimmed ends. So at first I will elongate the beam. It will be 12 meters. 12 meters, and the trimmed end won't be in the end, but I will use a no trimmed end, and I would like to work with the haunch because it's a saddle beam. So the first cross section, I will use this pen button and change the height of the cross section. So it's 900 millimeters at the beginning, and at the end will be 1800 millimeters. So I will create a new section, only change the height, and we are getting this haunch. I will turn off the reinforcement because it's bothering me right now, and the alignment of the beam will be to the bottom edge. So do that. Bottom. You can see I'm getting the symmetry of the saddle beam. Right now I copy operation. If I copy the operation, I select a master member. It's a member M1, and right now I'm working only with the master point and the insert point. So at first I have to reshape the cross section. So I will change the cross section at the beginning on 1800 millimeters and switch it to the section 2 like this. You can see, and right now I'm working only with a point as a master point and the insert point. The master point is on the member M1, so it will be number 3, and insert point is on the member M2 and it's number 4. So do that. And right now I have created a geometry with one boundary conditions, but right now immediately we will handle it. It's a simply supported beam, so I change at first the width of the bearing plate to 250 millimeters. I have to slightly shift it to the right, right. So can see now it's aligned. And I only copy this point support, use a master, which will be related to member M2, and it will be measured not from the beginning, but from the end. So right now, you can see the structure is still overdeterminate because I forgot to fix it in the X direction. Right now, it's a simply supported beam, and we can go to the openings. So use a plus button, add a new entity, and I can select some depth end or openings, but I would like to work with the openings. So the shape is recommended right now for our purpose circular with the diameter 1 meter. And I would like to have it in the middle of the span. So I only relate it to number 6. Right now I'm done with the middle opening. I copy the operation. I will change the diameter on the 0.8 and put it to the point, to the master point 0. So I will do that, and with using X and the Z coordinates, I will do the positioning. So the positioning will be in the negative way, in the negative direction, about 100 millimeters to the bottom edge. I will copy the operation and relate it to the member M2, only switch the members. Right now, I copy the operation again, and I would like to shift it, these openings about 1.5 meter from this point. So use this X direction. Yeah, I've got it. And right now, this geometry will be the same. It's symmetrical beam with symmetrical openings. So copy the opening number 2 and shift it about 1.5 meters to the left. So you can see it was very quick design of the geometry, and right now we can proceed to the loads. Let me switch back to the presentation. How I mentioned, we will do the design according to Eurocode. So what I would like to mention, what is important to know, that at this version we support the combinations or the code checks for ultimate limit state. For serviceability limit state, the combinations and mainly the code check will come really soon. So here are the combinations. This is the rule or equation for equation 6.10a and equation 6.10b, and these are prescriptions for doing the combinations. Yeah, and yeah, I come back to StatiCa detail, and we will do the loads. So what I would like to mention also, right now, if you use the template or you have some combinations for serviceability limit state, so you can't work with the pre-stressing. You can't work with the pre-stressing. You can see right now here is only permanent and the variable state or type, no pre-stressing. What you have to do, you have to clean all combinations at first and start from the scratch. And right now, the pre-stressing as a load case is available. At first, I would like to put self-weight. The self-weight will have some trapezoidal shape. You can start with the surface load or line load, because the self weight is not generated automatically, so have to be put it manually. And you can use surface loads or line loads. I prefer line loads, so I will do that like this. Some line load. And if I want to use trapezoidal shape, because here is a lower, or the high is lower than in the middle, so it has to be a trapezoidal shape which represents the self weight. So at the beginning is minus 5.5 and minus 10 kilonewton, and you can see I did this trapezoidal shape. This is this string. If you use it, you can do the trapezoidal shape. And for line load on the second part, I only change the member, you can see, and change also the line load minus 10 and minus 5.5. Right now, you can see I'm done. I'm done with the defining of the self weight, and I can proceed to superimpose dead load. It will be in the form of the uniform load, and will have the constant value along the height of along the length of the beam. So I create a new load case which will be superimposed dead load. It's really important to have a permanent type. Go to the load impulses, and also using a plus button, line loads with the intensity minus 26.2 kilonewton per meter. Also copy the operation and align it to member M1 on the top edge. So the other loads will be variable. So I create a new load case, which will be, I can extend it, which will be variable. For category H, it's a roof right now, and I have to change the load case type for variable. I can turn it off, the check, because I don't want to do the code check for load cases, but for the load combinations. But we have to fill it out, the load impulses, so it will be also in the form of the line loads with the intensity minus 4.1 kilonewton per meter. I only copy that and use it for member, for the second symmetry of the member or of the beam. You can see like this. Right now I create another load case which is variable also. It's a snow, has to be variable, and come back to the load impulses, create also line load with the intensity minus 4.3 kilonewton per meter. I copy the line load and change it to member M1. Also, I have defined the load case snow, and I think now it's time to define the pre-stressing load case. So I create a new load case. It will be pre-stressing. Name it pre-stressing. Turn off the tick. Oh, pre-stressing. And the load case type is pre-stressing. This is really important to sort it out correctly. Pre-stressing, and this load case is empty because the anchorage stress will be will be used in reinforcement. There you have to put the anchorage stress. So right now I will do the combination. Let me come back to presentation and explain what combinations we will do. At first, we will do the combinations according the rule, or according to equation 6.10a, 6.10b. But we have to distinguish between the short-term and the long-term state, because if you have a tendons, you have some short-term losses and the long-term losses. And due to the reason that we are not counting a TD analysis at this in the statistical detail, we have to ensure that the long-term losses will be included. So the long-term losses are represented in this coefficient, because we consider, or you can consider as average, 15% of the 15% of the short-term losses. 15% of the short-term stress. So this is the reason why the coefficient, or the factor, is 0.85 for long-term combinations. Let's do that. So I'll come back to detail, create a combination. The first combination will be ULS 6.10a, and it will be a short term. So you can see what is available is only ultimate limit state. Combination serviceability limit state combination will come later. So go deeply to the nonlinear combination definition, and we define the partial factor 1.35 for self-weight, 1.35 for superimposed dead load. The variable category of H is 0 for this combination, and snow is 1.05, and pre-stressing will be set as with the coefficient 1, or with the partial factor 1, because this is after short-term losses. I only copy the combination. The prescription rule will be the same, and I will define the combination 6.10b for short-term losses, or after short-term losses, 1.15, 1.15 for superimposed dead load. For variable load category H, the coefficient will be 1.5, and for snow will be 0.75, and the pre-stressing coefficient is 1, because we are talking about the short-term or the stress after short-term losses. Right now we'll do the stress in the tendon after long-term losses. It means I copy the operation. Sorry, I can delete this. I can copy the operation. You can see the factors, the partial factors are taken over. So I call it only ULS 6.10a long term, and change the pre-stressing factor on the 0.85. I will do that in the same way for combination 6.10b. So ULS 6.10b long term 0.85. Right now you can see I have defined four combinations, and I have to check all the combinations. Yeah, right now it works fine. Yeah, okay. Right now is we will proceed to the definition of the reinforcement and mainly the prestressed tendons. You can see I have defined, or I used before the templates, so some default reinforcement is being used, but I can go to the input and edit of the reinforcement and delete all. We'll start from scratch. And at first I would like to mention that you can import the reinforcement from the DXF, and also if you have some non-standard shape of the tendon, or some tendons which is, for example, for continuous beam, so it's better to use the import from the DXF, because it's more suitable. So at first I would like to define reinforcement from the point of view of the rebars. So I will create a group of bars. There will be one layer of the bars with the diameter 20 millimeters, and there will be 4 bars in a layer. The anchorage shape is straight at the beginning and at the end, but I would like to elongate these rebars to the end. So I will use this whole length and extension and elongate it. If we can see the 3D rendering of the reinforcement, you can see it's elongated, and it looks like this. Yeah, it's nice, and we can proceed to the definition of the rebars to the top edge or to the flange, right? So I can do the copy operation. There will be one layer of the rebars. The diameter will be 10, and it will be related to the top edge. So to the top, there will be 6 bars in a layer, and at the end I would like to, I know that this is a perfectly bonded, so I will use this perfect bond anchorage type. It's represented by this rectangle. I can copy the operation and very easily change it to the second member, M2. So I will do that, but what I have to change is the anchorage shape or anchorage type at the beginning. I have to switch it like this. Now it works, it's fine, and I can proceed to the rebars which will be in the web, because we have to use it because of the concrete is plain here, so we have to reinforce it. Some detailing rules have to be fulfilled. So I create or copy the reinforcement again. There will be 10 bars after 150 millimeters. Diameter will be 10, and only 2 bars in a layer. 2 bars in a layer. I would like to align it to the bottom edge, to the member M1. So to the bottom edge. Right now it looks like this. You can see I can go to the 3D rendering for better visualization. You can see 2 bars in a layer, which has a straight anchorage type. And you don't have to bother that this is the out of the section or out of the model, because we set some global cover and it's automatically cut it off the part which are out of the section. So it's very useful. Right now I create reinforcement in the form of the stirrups. If I will do that, you can see the group GB4 is automatically cut. I will change the model to 2D for better drawing or for better visualization for me. The diameter is 10. The first stirrup will be 50 millimeters from the beginning of the beam, and I would like to have 200 millimeters stirrups distances. So I did it right now, and I think now is missing only the reinforcement around the openings. So I will create around the openings. At first is automatically caught the middle opening. I elongate the diagonal bars 1500 millimeters. It's elongated. Let's see, like this. This is the wire fabrics, or the rebars around the openings are in the horizontal and the vertical direction, and also the diagonal because of cracks. So I copy the reinforcement around the openings and change the opening to member 2 and turn off the diagonal reinforcement, because for these openings I would like to use only the horizontal and the vertical reinforcement. Right now it's I will do that repeatedly for opening number 3, for opening number 4, for opening number 4, and for opening number 5 as the last one. You can see now I reinforced the beam, and it's time to put the pre-stressing. Let me come back to presentation and tell you something about the geometry of the tendons. Generally, the pre-tension beams has 1 or 2 layers of the pre-tension tendons, and one of the layer has some blanketed length. It means that the stress at this length it's not there and is shifted about some distance from the beginning and from the end of the beam due to the high bending moment around the support area. So this is the reason why the tendons are trimmed, or here in the model are trimmed, and it simulate the blanketed length. I will have 2 layers, one layer with 4 tendons and the second layer also with the 4 tendons, but it will have some blanketed length 1.5 meters, and the anchorage stress, this is the stress after short-term losses for our purpose, is 1200 megapascals. Let me come back to the model and continue with the definition of the pretension tendons. So I use a plus button, and you can see in the reinforcement type has been popped this or appeared this tail. It's a pre-stressing tendon. I will use it, and right now what we are getting, we're getting the material which we have selected, the pre-stressing type. We are working right now with the pre-tension tendons, but you know, we can work also with the post-tension tendons or mix. we can use a pre-tension tendons and post-tension tendon in one model. So pre-tension tendons, if I go to the 3D rendering, I can show you how the tendons looks. Instead of reinforcement rebars, the color is gray, and you're getting also some anchorage stress. So it means it's really important. These are the differences instead of or opposite to standard reinforcement. How I mentioned, there will be four bars in a layer. You can see 4 bars, and we have to align it to the bottom edge. So come back to the model. The definition will be by 2 points. It will be related to the master point M1. The master point is master point 1. The anchorage stress is 1200 megapascals. Also, the end position of the tendons is for the member M2 is related to the master point 2, and the stress at the end is to 1200 megapascals. And the first layer has some blanketed length, so it means I have to change the geometry of the tendon. So I shift it about 1.5 meters on the right, and the Z direction is 80 millimeters from the bottom edge, like this. And at the end, it's in the same way, but negative value in the X direction, and also 80 millimeters for Z direction. You can see this is the first layer of the tendons. I can copy the operation and change the Z direction. It will be, the increment is 40 millimeters, so 100 and 120, and there won't be the blanketed length, so we will start from the beginning at the 0 coordinates, and the end will be also at the end of the beam. So right now we have defined the geometry of the tendons with the anchorage stress, and it looks like this. This is my model, and let me mention differences, or why I'm talking about the anchorage stress. But in our case, this is the stress after short-term losses. It means you're putting there the stress after short-term losses. Why? Because we don't have some TDA analysis inside the application, so you have to use as your anchorage stress the stress after short-term losses. All the losses, the short-term losses, has to be included except the immediate elastic shortening, because it's included in the model. It's considered in the model. And for long-term, for stress in the tendons after long-term losses, we have used the coefficient 0.85 in the combinations. You can see here is the consideration of the 15% of the short-term stress, the loss, as the approximation. So let me come back to to the model, and we can proceed to the check. To speed up the process, I have pre-calculated the model and show you the results. So I'll open the model, and we can proceed to the interpretation of the results for the stage of the 28th day and for the stage construction stage at the end of design working life. Yeah, because how you know, we did 4 combinations, two for short terms and 2 for long term stress on the tendon. So it's being opened. Yeah, you can see this is my model. It's calculated, and we will show, or I would like to show the results, the code checks. In the code checks, the first window show you the summary of all results, where the extreme combination is displayed here, is ULS combination 6.10a for long-term effect, and the maximal utilization for ultimate limit state is for strength in the reinforcement, not for the pre-stressing tendons, but for the reinforcement. If we go deeply to the detailed check, you can see this is the stress redistribution on the concrete beam with the maximal value in the top on the flange. I can turn off the reinforcement and draw the mesh. You can see how it looks. So the maximal or the peak is here. And you can see also the redistribution around the openings, so it has a really big impact on the stress redistribution of the concrete. We can go to the reinforcement, where we are getting the maximal utilization. If I turn on the stress, you can see the stress on the rebars is really high. Is on the plastic branch 400 approximately 460 megapascals, and the maximum utilization is around the openings, yeah. Also I can display the stress, strain on the rebars, and also the ratio between the stress and the limit stress, and the yield stress or limit strain. We consider also the rebars in the tension. These red colors or red lines as our reinforcement under compression. Right now is we are going to the pre-stressing tendons. You can see I have the layer of pre-stressing, the first layer PT1 and the second layer PT2. So you're getting the coordinates with the maximal utilization. It's here. You can see it's also under the openings, 1463 megapascals. This increased value is caused by the variable loads, because the initial stress was, or increased stress was 1200 megapascal, as you know. What is really important, or is really nice to see, this transmission length. You can see how the stresses is getting increased. So it's represented at these elements, and I can read the results. I can read the results in the form of the stress, strain, and the ratio between the stress and the strain on the tendons. If we proceed to the anchorage, we can also do the code check if the reinforcement will be pulling out from the concrete or not, some bond stress. So this is my code check of the shear stress to design shear stress. And also I can display the force on the rebars, on each rebars. It's represented like this, so you're getting the forces in the stirrups. And the final part is auxiliary. At this part, you can display the default shape. For our purpose or our combination, this is it's not recommended combination for code check of the deflection or displaying of the deflection. The partial factors should be different, but you have the option to see the deformed shape. You can see for ultimate limit state it's 185 millimeters, but how I mentioned, it's not a suitable combination for seeing these deflections. I can see the tensor in the x direction, the deformation, and also in the z direction only, or the sum in the deformed shape. So right now, this is for this is a standard design of the pretangent beam, but you know, if you have pretangent beam, there are some construction stages, and you should do the code check in the stage at the pre-stressing. So it's in the 3 or 5 day, but at these days the concrete strength and also the modulus of the elasticity is totally different, because this is a time dependent material, and so it's more than recommended to change the material properties. How to do that? Let me come back to presentation. And in the presentation, I have my concrete grade is C50/60, and my assumptions was that I would like to do the pre-stressing at the 5 day. So it means according to code, there are some rules or formulas how you can count it, the compressive strength at some times for compression, for tension, and also the modulus of the elasticity. So this value will put into the model, but we also change the combinations, because at these days there is acting only self weight and the pre-stressing. So how to do that? Let me come back to our model. I will come back also to the loads and delete these 3 combinations, and I will keep only one combination. Yeah, it's let's say T5. I will call it like this. I can remove the snow. I can remove the variable loads, and I can also remove the superimpose dead load. What I have to do, I have to define the rule for self weight and the pre-stressing. So the factor will be factor 1 for self weight and the pre-stressing, and right now I can proceed to the definition of the time dependent material. So in the material models, if you go here, you can see this is your material model. We consider some compression softening, and here are some dependent value according to code. If you want to change it, you will click on this blue pen, and you will define the properties. The FCK at the time of the 5 day is 36.1 megapascals. You don't want to calculate this dependent value because you will put it manually right now. The modulus elasticity is 34,000 megapascals. The mean tensile strength in the tension is 3.1, and the 5% quantile is 1.9 megapascals. We are using parabolic rectangular diagram. Also, you can change it if you want to the second one, which is bilinear. If you have defined the material properties, you have to save it as some different materials. Let's say T5, and I will come back to the geometry. And in the geometry is recommended to control that we are using the edit material. It's here. Okay, perfect. And right now we can proceed to the calculation, the stage of the pre-stressing. So let me launch the pre-calculated example or project to speed it up and show you the results and show you that the pre-stressing works well. So I'm opening the model, and give me a second, please. Yeah, I'm here. Perfect. And go to the check. You can see I'm using the same model, but different combination and different material properties because of time. So you can see here is only permanent and permanent and the pre-stressing state. And here is my load case T5. If I go to the strength, I'm getting the stress, compression stress in the bottom edge. So it means that the pre-stressing works well because I have some pre-stressed, some compression stress, and this was assumptions to lift it up the beam. So the compression is on the different side than in the stage of the design working life. So it means at the end of the design working life, we can see also the reinforcement stress. You can see these rebars are under compression, and all are under compression mainly, except around the openings, the vertical one. So it's also guide you that it's correct. And we will check also the tendons. The stress in the tendon for PT1 and PT2 is approximately the same, but the value is lower because we don't have there the variable loads. You can see also it works well. But how to recognize that the pre-stressing works well are the deformation. So you can see these are my deformations with the maximal value 20 millimeters. The sec is 20 millimeters up, so it works well. I can also see the X and the Z direction. Now it's time to proceed the report, where is shown the diagram for a pre-stressing tendons. We are using a linear diagram with the hardening plastic branch. Also, the report can be exported to the Word document or to PDF, and the report or the output is customizable. So you can turn off and turn on some parts of the geometry, also turn on and turn off some parts of the loads as a combinations, or some reinforcement results, code checks. So as you can see, here are material models. This is the edited concrete, reinforcement, the description of the material for tendons, cross sections, geometry loads at 5-day, tendons with the anchorage stress at the beginning and at the end, and yeah, the results mainly for reinforcement and mainly for tendons are here. So you can see you have complete overview of all results, also some bill of the materials and the explanation. So I think that's it. That's it from my side. I will pass the word to Petya.
Thanks, Luki. Thank you for a nice demonstration and very detailed explanation of our new feature pre-stressing in detail. Let me present my screen.
Mm-hmm.
So we have a small time for Q&A. So we got several questions from you. I tried to answer them immediately, and I would like to share with the rest of you the most interesting ones. So that would be question for you, Luki. Can we calculate pre-stressing losses automatically in detail?
Yeah, this is in the plan in the future. This is in the plan, but we have it in the wish list and also in the plan for future development. So it will be there.
Thanks. You also asked about ACI checks, like the checks of pre-stress beams according to American code. This is also on our wish list, also like stability of a compressed flange of the beam. So we are continue with our development and would like to improve this feature pre-stressing in detail. And I have one, I would say, user experience with pre-stressing. So let me switch to detail. This is not detail, but it's right here. So I hope you can see the application. The user described that he wanted to test the pre-stressing, how it works, etc. And yeah, if you run the detail and try to model the pre-stressing on a template, for example, wall with openings, and you want to specify that this load case is a pre-stressing load case, it's not available like in this list. And this is because of the reason that you have defined also SLS combinations. So if we delete these two combinations, which were defined as SLS, like serviceability limit states, then it becomes available that this load case can be assigned to pre-stressing. And when you go to reinforcement, you can model the pre-stressing tendon, like because the user said that it was like inactive, he wasn't able to select it. So that was the reason. Be careful about this because the pre-stressing checks are available only for ULS, as Lukáš already mentioned. So this is all from the questions because we are short of the time. So I would like to go further. After the webinar, please fill in a short survey and give us the feedback about this webinar topic, etc. There will be also a recording of this webinar available on our website or YouTube channel. If you are a newbie, do not hesitate and get the trial. And for those who are interested in some educational material, tutorials, or already past webinars, visit our support center where we store a lot of useful materials. And as a last thing, I would like to invite you to our webinars and events. The next webinar is scheduled on 8th of December. It's going to be about steel, Connection Wednesday. The topic will be announced a little bit later. And an upcoming event is StatiCa User Day. I would like to show you our website where you can find the details. I will also try to share this link to this event with you. So right now you have it in your, you can find it in the chat in this GoToWebinar app. So on our website, ideastatica.com, you go to company and you can see the Global User Day. It's a virtual conference, so to secure your seat, you can register by clicking on this button. And on this web page, you can find the details about this event, why you should join us, and also what content we are preparing for you. So there are several sessions, mostly focused on Statica products, people, customer experience, and where we are heading. And as a last, we would like to announce a winner of Statica Excellence Awards, which is a contest with your users' projects which were registered for this event. There is still time for the voting, so if you want to support some good project, please visit this web page and select or vote for the best project or your favorite project. So, okay, this is pretty much everything from my side. So join us through the webinars and our events. Thank you for joining us today, and we wish you a good day. So calculate yesterday's estimates. Bye-bye.
See you. Bye bye.